Hi guys, Dr. Burns here. We're going to look at section 5.2 where we're getting a little bit more into how to calculate different theoretical probabilities. So the objectives at the top here, there's some blanks. Let's fill those in. One thing we want to be able to do is find the theoretical probabilities of random events. So how likely is it that something's going to occur? And then to find the probability of the complement, we'll learn what that means, of a given event, and to learn some basic probability rules. So make sure your cell phone is turned off so you're not distracted, and we'll go through these notes, listen carefully, and take good notes. First of all, what is an event? I've been using that term, but what do we mean by that? An event is the set of all possible outcomes of a given experiment to which a probability is assigned. So, for example, an event could be, or the event could be, I'm going to roll a die, and so all of the possible outcomes for me rolling that die would be my event. The die could land on a 1, 2, 3, 4, 5, 6, for example. I could flip a coin, so the event would be flipping a coin, and the events that are associated with that would be, the outcomes I should say associated with that would be that it lands on heads or it lands on tails. We generally use Latin letters, English letters, to denote events, usually uppercase, and the probability event, the notation we use for that, I'm going to write it over here, it's capital P and then parentheses, and then if it's A, for example, for the event, it would be like this, the probability of event A occurring. So the probability of an event A is always between 0 and 1, inclusive. So in other words, it can be 0 if the event would never happen, or it could be 1 if the event is 100% certain to happen. And so that's really important that you remember that rule. A probability is essentially a fraction or a percentage, like a 30% chance that it's going to rain. 50% chance that I'm going to land on heads, but it could be a fraction too, 1/2, 1/3, etc. It could be a decimal, 0.75, 0.3, but it cannot be a number bigger than 1. That's the important thing to remember there. The sum of all possible probabilities in an experiment, so in other words, all of those possible outcomes, the probability for each outcome has to add up to 1. So all of the different possibilities, the event or the probabilities have to add up to 1. That's the total. And so if I've covered all the events, it's got to add up to 1 or 100% if I'm using percentages. An event A has a probability of 0, like I was saying, 0 if it could never happen, and a probability of 1 if it is certain to happen. Those would be the extremes. So it can be expressed as a fraction, decimal, or a percent. So quick example, which of the following cannot be probabilities? Well, 110% because it's over 100%. 0.75 would be, I'm sorry, so it said cannot. Let me read the question carefully. So 110 cannot be a probability because it's too big. 0.75 is okay. 0.001 is okay. Now, what about 5.61? Can that be a probability? No, because it's larger than 1. And then how about negative 150%? No, because it's negative. But the others are okay. Now let's talk about the complement of an event. The complement of an event, so if it's event A, the complement is the event that A does not occur. You can kind of think of it like opposite, but it's the probability, or if event A is that it is going to rain, for example, the complement is that it is not going to rain. The notation that our book uses to denote complement is A, and then if that's the event A, and then like a little C is almost looks like an exponent or a superscript is really what it is. Some textbooks use a little prime notation, and sometimes I forget and use that as well, but our book uses this A and then the little C for complement. So the probability of an event and its complement, how are those related? Well, the probability that A does not occur would be 1 minus the probability that A does occur. Don't overthink this. If there's a 30% chance that it's going to rain today, that means there is a 70% chance that it's not going to rain today, right? You just did 100 minus 30 if you're doing percentages, or 1 minus the decimal. Equivalently, we could write this as the probability of the complement would be 1 minus the probability of the event itself. So look at this quick example, toss a fair coin. If A is the event that the coin lands on heads, then what is the complement? Well, first of all, the event, A complement, would be that the coin does not land on heads. And I know that that means tails, but I want to be really emphatic that it's the probability or the event that A does not occur. So if heads is the one we're interested in, the complement is that A does not occur, meaning it does not land on heads. All right, wait for a trolley outside the fort and note its arrival time. If A is the event the trolley arrives on time, then what is the complement? Now, notice I didn't ask you for probabilities in either of these questions. I just asked you for the event for itself, the complement. So the complement would be that the trolley, or the event that the trolley does not arrive on time. You could say that it arrives late. I understand that that would be the only other scenario. It's either on time or it's late, but that's what we're going to say. It's not on time. I guess you could say, actually in that case, I guess the trolley could arrive early potentially. So it's always better to state the complement in the negative if you can. The trolley does not arrive on time would be the complement of that event. All right, let's talk a little bit more about sample space. So the sample space is the set of all possible equally likely outcomes in an experiment. So the sample space are all of the different outcomes that could occur. And any collection of outcomes in the sample space could be a given event. For example, let's say we're talking about rolling a die. So the sample space, if it's a 6-sided die, would be 1, 2, 3, 4, 5, 6, right? So here, let me write that down here. So rolling a die, for example. The sample space would be, we could write it as 1, 2, 3, 4, 5, 6. And then a given event from that sample space could be that we roll a number that's even. And that's, so you can kind of think of like that, a sample, or an event rather, as a subset if you want to. Don't get too hung up on all these vocabulary words. Once we start getting into some practice problems, we're going to be focused on actually calculating probabilities, the formal terminology. As long as you recognize what to do and you see it, it's not going to be as confusing as maybe it seems right now. So just hang in there and let's talk about a few different probability rules and how we can kind of put this together. Combining events with the word and. So when you see the word and in a problem, that means that the event belongs to A and B, meaning it must belong to both A and B. If you kind of think of it as sort of a Venn diagram, let me come down here and write a Venn diagram. If this is event A and this is event B, the and scenario means that the event you're interested in is in both categories, A and B. On the other hand, if you see the word or, that's a little different. That means that the event can belong to A only, or B only, or it can be in both. So or is sort of everything that could occur, right? So in my A and B Venn diagram, A or B would be all of this plus all of this, A only or B only, or both, right? So my or in that case, A or B, would be everything in that Venn diagram. If it happens that there's an event where there are no common outcomes, in other words, events that cannot occur at the same time. So in other words, in a Venn diagram, if this was A and let's say this was B and there was no overlap between them, that would be an example of events that are what we call mutually exclusive. Now, this is a term you want to be familiar with, so put a little star by this term because this is one you want to recognize. And if you want to add this picture to your notes, these would be events that are mutually exclusive. Notice that there is no overlap, is what I'm saying. Okay, that means the events are mutually exclusive. They cannot occur at the same time. So why is that important? Well, when we have a question involving or, this is something we need to take into account. So the probability of A or B, if I'm asked to calculate the probability of A or B, that would be the probability of A plus the probability of B minus the probability of A and B, where they overlap, occurring. If it happens that the events are mutually exclusive, then this formula, what happens, let me ask you this. If the events are mutually exclusive, then this part of the formula would be what? A and B, the probability. Well, if they're mutually exclusive, there's no overlap, right? So this part of the formula just becomes 0. So the probability of A, if A and B are mutually exclusive, the probability of A or B becomes just the probability of A plus the probability of B. I think what might be helpful here is to just remember this little formula. And if it turns out that the events are mutually exclusive, and that's what this little remark says here, that if A and B are mutually exclusive events, they can't occur at the same time, so this becomes 0, then this part of the formula goes away anyway, and it doesn't matter. It's really just one formula, not two entirely separate formulas. But that idea of mutually exclusive events is going to be very important. And we'll do some examples of this in class. It's just something to consider when you're looking at an OR probability. So bring your notes with you and we'll do some practice with this. I'll see you in class.